Okay, this is example 9.14 from your textbook. Given a steel wire 60 foot long is strained to 0.00067 inch per inch, find the total elongation. That's the deformation or the stretch of the wire. So we're going to start with the definition of strain. Strain equals deformation divided by the original length. We're going to use that equation to calculate what the deformation is. Okay, we rearrange the equation to solve for the deformation. We take our strain, which is unitless inches per inch, times 60 feet, and then convert the 60 feet to inches, and then we solve for the deformation. Okay, so the interesting thing about this is we have a wire that's 60 feet long, and then when we put this load on it, it actually grew in length by almost a half an inch. Okay, next example. 917. In this case, we have a tensile member for a machine part. A machine member is loaded as shown. It's essentially a hollow tube that's subject to a tensile load. The material is steel, and from that we know that the modulus of elasticity is 30 times 10 to the 6 psi, and it has a proportional limit of 34,000 psi. Find the tensile stress and find the total deformation. Okay, this is the solution. First we need to find the area. The area of a hollow tube is pi over 4 times the outside diameter squared minus the inside diameter squared, and we calculate 0.245 square inches. Next, we're going to calculate our deformation. Deformation equals the load times the length divided by the area divided by the modulus of elasticity. We substitute our values in the equation and we calculate 0.0204. That is the deformation for this part under that load. Now we need to calculate the stress. P equals stress equals P over A equals 20,400 psi. Okay, so why did we calculate the stress? Okay, so for the deformation equation to be valid, for this equation to be valid, we need to assure that we are operating in the elastic range. That's why the problem statement gives us the elastic limit of 34,000 psi. So we calculate what our tensile stress is, and it's below the elastic limit. Therefore, the stress is less than the proportional limit of 34,000 psi. Therefore, the calculated deformation of 0.0204 inch is valid. So we need to make sure that our stress is below the proportional limit for the deformation equation to be valid. Okay, let's go into chapter 10. First problem here is we've got a results of a stress strain curve, tensile test, if you will. It gives us 2 points, point A and point B. We have strain and we have stress at those 2 points. Find the modulus of elasticity, and then also find the stress that corresponds to 0.02 strain. So part A, the 2 data points were taken from the graph up to the proportional limit. These were the 2 points. The modulus of elasticity equals the slope of the line up to the proportional limit. So therefore, we're just going to take the slope of that. Change in stress divided by change in strain, and we end up with 30,000 psi. That is most likely steel. Okay, example 10.2, we're going to calculate what the percent elongation is. Yeah, you can find this one in your textbook. I'm going to have to fix that one. 10.3, allowable stress. Given an ASTM A36 steel rod 6 meters long, must be capable of supporting a tensile load of 11 kilonewtons without elongating more than 7 millimeters or exceeding an allowable tensile stress of 150 megapascals. The proportional limit is 234 MPa. Find the required rod diameter to an increment of 1 millimeter. So first, what we're going to do is find the minimum required area based on the allowable stress. And that A equals the load divided by the allowable stress, and that equals 73.3 millimeters squared. Next, we're going to find the minimum required area based on the allowable elongation. We're going to use this equation right here, and we're going to calculate an area of 45.5 millimeters. Okay, so now we know that the largest required area is based on the allowable stress. So we're going to use that 73.3 millimeters. What we're going to do is we're going to calculate the diameter based on 73.3, and we get 9.66 millimeters. Therefore, we're going to use a 10 millimeter diameter rod. And then our last problem has to do with factor of safety. Given the results of a tensile test, it shows that the tensile strength equals 60,000 psi and the yield strength equals 36,000 psi. First of all, find the allowable stress to yield strength with a factor of safety of 1.6, and B, the allowable stress to ultimate strength with a factor of safety of 2. Here's our solution. Factor of safety equals yield stress over allowable stress. So therefore we got 36,000 psi divided by 1.6. So therefore it's 22,500 psi. And then for B, the allowable stress equals the tensile strength divided by 2, which is 60,000 psi divided by 2, or 30,000 psi.